is Director of Product Management with ZV Incorporated. Art is a skilled and highly experienced product manager with about 25 years of experience in bringing these products to the market and ensuring that he has successes in the marketplace. So I think he's a very talented cross-functional expert or team leader, and I think he will give you a good insight into the topic today. Art, it's all yours. Thank you.
Thank you. So I would ask everybody to please move closer. I'm going to be showing some schematic diagrams on this screen with really fine prints and lines, and you may not be able to see and understand if you're way in the back. I really want you to get the most out of this today. So thank you. Is this microphone working okay? Can you hear me? Okay. I can't hear myself, you know. Awesome.
So you're just 10 to 15 dB above the from the previous.
All right, let me turn this on and see if I can get it to work. Yes. There we go. All right, so once again, my name is Art Weeks. I'm the Director of Product Management at ZV. I've been with ZV a little more than 6 years now, and dealing with the AV product line, the network product line, that entire time. My background before that was kind of the printer and copier industry, which, believe it or not, has a lot of similarities to the AV industry in terms of moving data around a network. So the agenda for today, and we're probably only going to run about an hour or so, so it's not going to run the full 90 minutes. We're going to talk about network and switch basics. That's going to probably be 20, 25 minutes. Then I'm going to get into some AV network examples, and every example that I show you is going to be a real example of a customer deployment using ZV equipment. Most of it, I think, I'm showing designs that are based on a 10 gigabit network. And then very briefly at the end of kind of a final wrap up, probably only 5 minutes or so, is kind of what I call a network design prep, how to be ready for diving into your network design. Okay, the things you need to have, you know, kind of handy. All right, I think we can skip past this slide. This is kind of the details of what I'm going to cover in part one. So let's just get right into it. So AV network design. Really, at the end of the day, it's math. It's really just math. Understanding some basics about networks, about network switches, about encoders and decoders, about duplex communication. These are the things you need to understand and know to do an AV network design. So let's start with some switch basics, something called a backplane. Maybe you've heard this term before within a switch. So a backplane measures the total amount of data that a switch is capable of transferring kind of simultaneously. Sometimes you see different terminology for a backplane. I put one up here called, is my little laser pointer working? I'm going to say the laser pointer is not working on this. Exchange bandwidth is another term you'll sometimes see for a backplane. The higher the backplane bandwidth of a switch, the stronger the ability to process data. But in most cases, like most things in the world, more capability is more cost. So let's talk about some backplane terminology. There's two different terms here. Something called interface throughput and backplane throughput. So interface throughput, again, I wish it were working, is the throughput through an individual port. So one network port that you're plugging into the switch. What is the maximum bandwidth on that port? And you'll hear the very common terminology might be a gigabit port, or a 10 gigabit port, or a 40 gigabit port, or even a 100 gigabit port. That's the maximum throughput on that individual port. And it's not speaking to the throughput of the actual switch, it's just that individual port. Now the backplane, again, is the throughput of the entire switch itself. It's get into a little more detail on that in a bit. So again, backplane throughput, the entire device sending and receiving on all ports simultaneously. So a switch might have 20 ports or 48 ports. Actually, 40 and 48 are very common sizes for network switches in the 1 gig and 10 gig land. So it's that throughput through all of them at the same time, assuming you had a device plugged into every single port, which is sometimes common. Switches get filled up. All right, so let's take a look at just a simple example, and I'm trying to keep the math really simple here. And we're going to assume, I think in all of my examples today, that we're talking about 10 gigabit networks, 10 gigabit switches. That means, as a general rule, the individual ports are 10 gigabits. So at the top here, we've got an example of a switch, and I've got 2 devices connected to it. And so each of those devices has that maximum throughput, again, of 10 gigabits each. And for this simple example, it's a 20-port switch, and we're going to assume a backplane capacity of 100 gigabits, which means that the switch itself can handle 100 gigabits of total capacity. So if you look at the top diagram, 2 devices are connected. You notice that I've colored them green, which indicates they can flow at their full rated throughput, 10 gigabits. If you add them up, it's 20 gigabits. The switch can handle 100, so that's not a problem. We look at the drawing down below there, same 20-port switch. Again, each port is 10 gigabits. Well, 20 times 10 is 200 gigabits. If the backplane of this particular switch is only 100 gigabits, then this is a scenario that cannot work. Does it mean things aren't going to work entirely? No. Things are still going to work to some degree, but it means that each port can't run its fully rated bandwidth. So hypothetically, if each port ran at only 5 gigabits, half of its total possible throughput, then the backplane could handle it because 20 times 5 is 100. Does that make sense? All right. So you'll see this concept of blocking versus non-blocking backplanes. Okay, or blocking versus non-blocking switches. So in a perfect world, a network device can provide full bandwidth, that full 10 gigabits, and this, the examples that I'm using, on every single port simultaneously. Okay, and that's what's called a non-blocking backplane. The switch can handle as much as you throw at it on every single port, no matter what. Okay, non-blocking backplane. And as a general rule, that's what you want to be looking for. You want to be purchasing a switch that has a non-blocking backplane, or switches that have a non-blocking backplane. We'll get into interconnecting switches in a little bit. So, as the name might imply, a blocking backplane cannot provide full bandwidth on all ports simultaneously. It can either provide full bandwidth on some ports, or it can provide partial bandwidth on all ports. All right? Again, that's a thing you really want to avoid. So let's take a look at, again, a teeny bit of math here. So our 20-port switch example, 10 gigabits capacity in each port, but only 100 gigabits would be a blocking switch. So that a blocking backplane. To be non-blocking, our switch would actually need to be 400 gigabits capacity for the backplane capacity. So you might be looking at that number that I've highlighted there in red, 400 gigabits, going, how did he get 400 gigabits when 10 times 20 is only 200? Well, that takes us to an important concept of network communications. So, answering the question, it comes down to the fact that the manufacturers are going to specify transmit and receive independently. So any port on a switch needs to both be able to transmit and receive at that full bandwidth at the same time. So a 10 gigabit port is really capable of 20 gigabits of communications at any given moment. 10 in and 10 out. And when you're calculating the backplane, you need to account for both. So really the answer becomes 20 ports times 20 gigabits per second, so 400 gigabits to be a full non-blocking backplane. So again, a lot of simple math. All right, so how do you determine what the backplane is of a switch? Really the easiest thing to do is just look at the data sheet for the switch. They will 99% of the time tell you in the spec sheet. But again, they might use different terminology. So terms that I've seen: fabric bandwidth, backplane capacity. This is an example here. This is a Netgear M4300-96X. It's a 10 gigabit switch. It has 48 10 gigabit RJ45 ports, or copper. And it has 4 SFP plus ports that are shared. We'll get into that in a minute. SFP plus implies fiber, so fiber optic ports. And it has a 960 gigabit per second non-blocking fabric across 48 ports. So if you take that 48 times 20, that's where that 960 number comes from. So this is a fantastic, fully non-blocking 10 gigabit switch. It's actually one of the switches that I highly recommend and shows up in lots of the ZV designs that I work on, for lots of reasons. Not just that it's fully non-blocking. One big reason I'll get into a little later is it comes pretty much pre-configured for AV equipment. So, as I pointed out on that last slide, there's a concept of shared ports. What is a shared port? What does that mean? So if you look at this particular switch on the bottom there, it has 48 copper ports, again, that RJ45, and then 4 of the SFP ports. So again, if I had the laser pointer, I'd point to it, but on the bottom, on the very far right, you see 4 ports, 2 on top of each other, that look a little bit different than the other ports. Those are fiber optic ports, where you'd put an SFP plus module in there to connect either multi-mode or single mode fiber. Those are shared. So technically, this 48 port switch has 52 ports. 45 RJ45 and 4 SFP. The SFP ones are shared. What does that mean? That means that if you use them, you need to give up using a copper port, an RJ45. So you can only ever have 48 active ports. So if you use the 4 fiber ports, now you only have 44 of the RJ45 copper ports you need to give up for. Okay, so you always have 48 is the maximum. That's the concept of a shared port. Some switches will let you select which port it is, the ones that you're giving up. Some switches will say these are the ones that you can't use. So you just need to, check the documentation for your switch. Okay, so that was some just kind of very high-level basics about kind of a switch itself and a backplane. Let's talk about a LAN. So a LAN just stands for local area network. Okay, and it's a collection of devices, usually in one physical location. A LAN can be small or large. You can have a LAN that's a single switch. You can have a LAN that's dozens of switches interconnected to each other. Okay, so you can have from 2 devices to thousands of devices connected to a LAN. An important concept within an AV network, and I go into this in more detail in a different class, is for any 2 devices to be able to talk to each other directly, they need to be on the same LAN. They need to be able to see each other, and they need to be on the same network, the same LAN on that network. If they're on a different LAN, they're on a different network, then they can't see each other, they can't talk to each other. So you can't, for example, in an AV world, route video from an encoder to a decoder that's on a different network. Okay, that's not 100% true. There are cases when you actually can do that, but we're not going to get into advanced networking. All right. There's also a concept of something called a virtual LAN or a VLAN, okay, which is a way to logically kind of segregate devices on a network. And it follows that same principle that devices need to be on the same VLAN to see each other, even if they're on the same switch. So in this example, we've got switch A and switch B that are connected to each other, and we've created two different VLANs, the green VLAN and kind of that orange VLAN. You notice there are ports from both switches that are on each of the two VLANs. So for devices to talk to each other in this case, not only, it doesn't matter if they're on the same switch or not, they need to be on the same VLAN. So anything in the green category can talk to something in green, anything in the red category can talk to something in red, but red cannot talk to green and green cannot talk to red. Okay, so it's a way of, again, segregating off. A lot of customers like to do this with their AV traffic, meaning they want to have the AV traffic on their primary corporate network, but they want to segregate it from the regular traffic on the network. They don't want it sharing bandwidth or space with email and whatever. So they VLAN it off, so only those particular AV devices can talk to each other and can't see the other parts of the network. Okay, so I kind of hinted at this a little bit earlier, kind of a concept of full duplex versus half duplex. So what full duplex means is a device can send and receive information simultaneously. And this comes into play a lot when we're talking about an AV network, because it is often a requirement the device is doing both at the same time. Sometimes it looks pretty one-directional, and a lot of the communication is one-directional, and we'll talk about that when we get into the actual design stuff in a few minutes. So there's that concept of half duplex. So half duplex means I'm either sending or I'm receiving, but I'm not doing both, and I can't do both at the same time. So this is going to come into play, as I'll show you in a moment. It's very important when you're interconnecting switches to each other, understanding this concept. So again, this is just another quick example. So an example of full duplex would be a telephone call. You can talk and listen at the same time, and people on both ends can do the same thing. Half duplex would be more like a walkie-talkie situation. You need to press a button to send and release the button to listen. All right. The most simple AV network design you're ever going to do is a small deployment where you can have all of your endpoints on a single switch, meaning you don't really need to worry about any math. You plug all of your devices in, assuming that it's the appropriate switch. If you're plugging in 10 gigabit devices, it needs to be a 10 gigabit switch. If you're plugging in 1 gigabit devices, it needs to be at least a 1 gigabit switch. It could be a 10 gigabit switch, but that's kind of overkill. Anyway, long story short there again, you're going to plug in all your devices, all of your encoders, all of your decoders, your control system, everything else. It's on one switch, it's in a rack somewhere, it's just going to work. You don't need to worry about math, you don't need to worry about a design, it's just there. So, and this happens a lot. I see plenty of small deployments, like this is a 48 port switch, so maybe there's 10 sources and 20 displays or something like that. Gets on one switch very easily, no problems. But we're going to talk about designing some AV networks that are going beyond a single switch. So you need to understand some concepts. So this is a representative network design here. On the left, you have our encoders. They're connected to your sources. Your sources can be anything. Satellite receivers, media players, laptops, cameras, whatever. Those are going to come into an encoder and get put onto the network. As a general rule, encoder data flows into the switch. That's the direction it's going. Then you have your decoders, which are going to be connected to your displays, your projectors, your video walls, your touch panels, whatever they happen to be. That's the decoder. And as a general rule, decoder data flows out of the switch into the decoder. So encoder into the switch, decoder out of the switch. Again, not always. There are instances where the data can be flowing in opposite directions, but as a general rule, that's where the bulk of the data is going, in or out, depending if it's an encoder or a decoder. You got to keep this in mind when you're designing a network. So one thing I always tell people is assume worst case bandwidth. So if I've got an SDVW encoder, which is capable of outputting 10 gigabits per second, really just below that because we draw a line, but you should assume that it's always outputting 10 gigabits per second, unless you have reason not to assume that. Same for the decoder side. An SDVW decoder can receive 10 gigabits of bandwidth. You should assume that it always is, unless you have a special reason to know that it's not. I'll show you some examples of both of those when we get into the actual network design, so I'm going to show you. How much data are we talking about? I've been talking about a 10 gigabit network. When would that ever come into play? 10 gigabits is a lot. Well, you'd be surprised. Video data is huge, especially uncompressed video data. You'll hear of two different types of products in the AV industry. Uncompressed products, which require a 10 gigabit network, and compressed products that run on a 1 gigabit network. Whenever you hear of a device or an AV network being a 1 gigabit network, you immediately know it's compressed. It's just a fact, because look at the amount of data we're talking about. If you look at old HD, 1280 by 720, which isn't all that common anymore actually. 60 frames per second, 444 chroma subsampling, that's 1 gigabit per second all by itself. So to run that on a 1 gigabit network, you're going to need to compress it. Go up to full HD, 1920 by 1080. 60 frames per second with a 420 subsample. That's 1.5 gigabits per second. You go to a 422 subsample, 2 gigabits per second. These are all approximate numbers, by the way. These aren't the exact numbers. You go to 444, now we're around 3 gigabits per second for that data. You jump up to 4K. There's a lot of 4K stuff out there. 3840 by 2160, 30 frames per second, 444. That's 6 gigabits per second all by itself. Actually, a little bit more than 6. If you go to 60 frames per second, 420, that's the same 6 gigabits per second. You take that all the way up to kind of the worst case scenario for an HDMI 2.0 specification. 3840 by 2160, 60 frames per second, 444, so no chroma subsampling at all. That's over 12 gigabits per second all by itself. So even that, to get onto a 10 gigabit network, needs to be compressed. So we actually compress that down to a little less than 9 in our environment. So it's a lot of data. So again, assume worst case scenario when you're designing your network. All right, I'm going to show you two different examples back to back here. They're pretty much the same exact design. One design was done properly. I'm calling it the bad example. Then I'll show you what I call the good example, doing the same exact design the right way. And this is very simplified, overly simplified for training purposes here. So let's say you've got a 16 by 64 configuration. I'm going to use 2 Netgear 48 port switches. Okay? By 16 by 64, I mean we have 16 encoders, 16 sources, and 64 decoders or displays. Here we've got 2 switches, switch A and switch B. And we know we need to interconnect them so they can share data among each other, right? And we're going to have, in this example, 8 interconnects between the 2 switches. Each port is 10 gigabits per second. So if we've got 8 interconnects, we've got 80 gigabits per second of bandwidth between these 2 switches. And it's bidirectional. So 80 gigabits going from A to B, and 80 gigabits going from B to A. So, as I said, this is overly simplified, but this is real world. I've had an integrator do this exact same thing, not with these exact numbers, but this exact scenario. So they go on site and it's time to install the equipment because they didn't pre-install this stuff, in their lab or whatever before bringing it out to the customer site. They get on customer site, they got all the equipment, they start plugging it in. They get their 16 encoders, they plug them straight into the first switch they see. Then they take the first 24 decoders and plug them into that same switch. It's because they can get 40 endpoints on each switch here because they used up 8 ports for the interconnect. Okay, then they take the remaining 40 decoders for the 40 displays and plug them into the other switch. And everything seems fine. They're going to start testing their system like any good integrated would. You're going to make sure it works before you walk out on your customer, right? And they start routing video from those sources to displays. And on the top switch, they're routing to those first 24 displays and everything works fine. Everything's always going to work when you're dealing on a single switch with a non-blocking backplane. You're never going to run into a bandwidth problem. So that's all great. And then they start routing video to some of the displays on the bottom switch, those 40 down there. And they can route, 1 stream, 2 stream, 3 streams. We'll assume worst case here. So every stream is 10 gigabits. 4 streams, 5 streams. You can route those 5 streams to all 40 of those displays. It's going to work fine. You have enough bandwidth to do that. 6 streams, 7 streams, still working great. Looks good to me. They wrap it up, they leave the customer site. Customer gives them a call back a couple days later. Sometimes when we're using this AV system, some of the displays stop working. We start getting junk, artifacts on the screen because you don't have enough bandwidth to get everything there. What happened is, as soon as you start sending a 9th stream, a 10th stream, an 11th stream between those 2 switches, there's not enough bandwidth. You can't send 100 gigabits over an 80 gig link. You'll get the 80 gig, but it might not be exactly what you want for each of the displays, and it's not going to work. So you start getting artifacts. So really, if we look at this here, you have a need for up to 160 gigabits flowing into that switch there from those encoders, 10 times 16. You have a potential need for all 160 gigabits to flow between the 2 switches, but you only have 80 gigabits of bandwidth to do it. So you don't have enough. How do you solve this problem? So let's take a look at the good example. Same exact setup, 16 by 64. Same 2 switches. Same 80 gigabit interconnect between the 2 switches. This time, you're going to configure it a little bit differently. You're going to think about it ahead of time. You're going to make a plan. And I'm all about that, making a plan, understanding what you're doing, understanding the direction things flow. So I'm going to connect 8 sources to that top switch. And then 32 displays, 32 decoders. I'm going to do the same thing down the bottom. I'm going to have 8 sources down the bottom and 32 displays. Now I can start testing it. Testing those 8 sources on the top. Of course I can send them to any of the 32 displays on the top switch because we're on that same switch still. You're on that non-blocking backplane. You're never going to see a problem. Now I want to route those videos down to the bottom switch, to those other 32 displays. And because I've got 80 gigabits worth of bandwidth between the 2, I can send all 8 streams to that second switch. I've got enough bandwidth to do it. Then I can start testing the bottom stuff. Those 8 sources on the bottom switch can go to any of the 32 displays on the bottom switch. Again, same switch, non-blocking backplane, never going to have a problem. I want to send them up to the 32 displays on top. Again, I've got enough bandwidth now to do it. Maximum I'm going to need is 80 gigabits. I've got 80 gigabits available. So again, up to 80 gigabits of data flowing into the switch from each side. And then 80 gigabits, the key here again, bi-directional. I can have 80 gigabits going up. At the same time, I've got 80 gigabits going down. This is a difficult concept sometimes to grasp, so I can do both at the same time. Again, potential need for 80 gigabits to flow between the switches. I've got enough bandwidth here. This design would work. Again, overly simplified. I'd probably actually give myself some overhead here and give myself more than 80 gigabits in this example. But it's showing you how you have this need to understand the direction that things are flowing when you're planning out your network design. Knowing that data, again, is coming from an encoder into the switch and coming out of the switch to a decoder. All right, so we're interconnecting switches to each other. And there's kind of two really standard ways of doing it. There's something called stacking, and there's something called link aggregation. So stacking, I'm actually showing both of them here. Stacking means you're going to interconnect the switches in a way that they're seen as one big switch. So it's going to act as one switch in your network, and you can control and manage it as one switch. Link aggregation is a means of connecting out to another switch, usually with more than one port. And the switches are intelligent enough to break up the data and share it between those multiple ports going to the other switch. Okay, and there are benefits and drawbacks to each way of doing things, which I'll show you really quickly here. So let's look at stacking first. So again, stacking is when you're treating it as one big switch. So big pro, ease of management. You have what's called a stack master. In this group, in this example, there's 4 switches together. So one of those 4 would be the stack master. All you need to do is log into that one stack master to manage the entire stack. You get redundancy. So a typical stack design is what's called a ring stack. And it might be hard to see in this picture. And again, I wish I had my laser pointer working. But if you look at the green lines there, the top switch goes to the second switch down. The second switch goes to the third switch. The third switch goes to the fourth switch. Then the fourth switch goes back up to the first switch. So it creates a big loop. Okay? So that gives it a level of redundancy in the system. If something were to break, if a switch in the middle were to break, for example, the connection could work its way back around the other way. Okay? So stacking allows for redundancy in a system, which can be a big benefit in a network design, although I very, very rarely see redundancy designed into the designs that I work on. Most customers just don't need it. And quite honestly, for the most part, networking equipment is amazingly reliable. These things are built to be turned on and run 24/7 for years. Okay, stacking cons. Scalability. It can only be so big. In this example, I'm using Netgear, and in the Netgear example, I can only have 8 switches in a stack. Flooding. This is kind of an advanced topic. Flooding of multicast transmissions in a switch stack. So the switch, because it's trying to act as one big single switch, is trying to send every signal everywhere all the time, which isn't necessarily what you want to do in an AV environment. So that can lead to something called flooding of ports in the switch stack, which basically means your stack isn't working properly and you're not getting the AV data where you want it to go. I'll talk about flooding a little bit more later. So let's look at link aggregation. So the pros, scalability. You can pretty much scale as much as you want if you have enough ports. Netgear supports up to 128 lag routes on some of their switches, which is a huge difference to an 8-switch limitation. Efficient handling of multicast traffic. So Netgear uses this concept called IGMP+. IGMP is a completely different topic I teach a class on, to prevent multicast flooding access lags. And they suggest 98% of the time to use a lag aggregation design instead of stacking when you're using their switches. I'll show you examples of both in a little bit though. So cons, there's always a con, isn't there? So manageability. If you've got 20 switches in the lag, you need to individually log into all 20 switches to manage them and set them up. So that's more of a time issue than anything. and a lack of redundancy. So it says, I mean, I say you cannot create a redundant core like you can with stacking. That's not 100% true, but it just becomes more problematic. All right, some of the basics before I get into some of the actual designs. Power over Ethernet. Everybody's probably heard of the term PoE, power over Ethernet. I love PoE. PoE is fantastic. I hate the concept of having to plug in a power supply for anything. I just want to plug it into the network switch and be done with it. In the 1 gigabit world, PoE is the standard. I think it's actually difficult to buy a switch these days that's not PoE, and I wouldn't. Always buy a PoE switch. Even if you have devices that aren't PoE, you're certainly going to have devices that are. And a lot of devices that you get these days that are PoE, like an AV encoder or AV decoder or any other piece of AV equipment that plugs into a network, if the device supports PoE, oftentimes they don't even ship a power supply for you in the box, which means if you don't have a PoE switch, you need to buy a power supply separately. So again, PoE, so it provides the power over the network cable. PoE budget. This is something you do need to consider. A switch is going to have a power supply associated with it, and that power supply is going to be rated for a certain number of watts. Some of those watts need to go towards powering the switch itself, and then some of those watts go towards what's called the PoE budget. How much power do they have to put onto those ports on the switch? So I have an example here of a couple things and some information. So you might hear different terms, PoE, PoE plus. What PoE means is up to 15.4 maximum watts per port. PoE plus is up to 25.5 maximum watts per port. There are some other differences as well. I'll get into that in another slide. So let's have an example. This is a real switch. This is a Netgear switch, 1 gig, GSM 4230PX. So it's 24 PoE plus ports and has a 480 watt PoE budget, which is good. So that works out to a budget of, some simple math there, about 20 watts per port if you were to use, every port on the switch simultaneously. But if you look at what PoE plus is 25.5 as a maximum times 24 ports. Well, that's 612 watts. That's beyond the budget for this particular switch. So what you need to do is know what the power use is for every device you're plugging into that switch. Then you add up that total to come up with the budget that you need for the switch. So if you have devices that are hypothetically, let's say 10 watts, you can plug them all in and never worry about it because 10 times 24 is 240 watts, you got plenty. But if you have devices that go over, when you start getting over 20, that's when you have to start worrying about the math. Okay, if all your devices are under 20, no worries, plug them in. So some other interesting kind of tidbits to tell you about PoE. So in a quote unquote PoE switch, and actually you don't see too many switches that are just plain old PoE anymore. They're all PoE plus. But on a standard PoE switch, again, up to 15.4 watts, the power that it's supplying out the port is negotiated at the initial connection of the device. So it's going to figure it out right away, and then it's going to supply that same power all the time. PoE plus is a little bit different. Not only does it go up to 25.5, but power is negotiated initially, and then it's negotiated in 0.1 watt increments continuously, which means the power can fluctuate up and down as needed, which can happen in an AV device, an encoder or decoder. The amount of power it's using can move up and down depending on what it's doing. All right, that was part one, kind of switch basics and stuff. Any questions here before I move on? And please, as I'm going through this, if you have a question, just jump right in and let me know. We can, get interactive however that you like.
Does the lag consider as uplink as well?
The lag? So a lag is, it's bidirectional like anything else. So I'm going to show you some examples here that hopefully will answer any questions you might have regarding that. So I'm going to get into a bunch of examples here: single switch, spine leaf, limited connections, dual switches, dual spines with limited connectivity, redundant dual spines. And I might make use of this little whiteboard here to draw up some stuff, especially if you have questions. I think it's great to visualize things, to learn. So let's take a look at some simple designs here. So this is a design, very simplistic, small design, single switch. Customer had 13 workstations. It's really hard to see that. Man, I wish I had the laser pointer. But 13 workstations connected to encoders, some using USB, some not. And then they had a single LED wall with an LED controller. They had a keyboard mouse coming back over USB, for KVM functionality. They had a manager's display, again, using KVM down there as well. And the total quantity of devices, encoders, decoders, etc., was less than the number of ports on this particular switch. This switch here, really hard to see in the middle there, it's a Netgear 4396X, so it has 96 ports on it. I love this switch because 96 is a great number. That's a lot of ports. You can do a lot of designs in that single switch. So again, simplistic. You don't have to worry. Plug in all your devices, no math involved, fully non-blocking backplane. This just works. Doesn't get any easier than this. All right, what do we got next? All right, so this is a spine leaf design. What that means is spine, you have a core switch that is then connected to leaf switches. So spine and leaf. Leaf are the independent switches around the side there, labeled 1, 2, 3, 4, and 5. In this design, I'm just getting closer so I can see some of the numbers. So if you look at number 1, the main head end, that has 35 encoders connected to it. And obviously those are 10 gigabit connections. And we assumed worst case again. As in most of these designs, they assume worst case. So if I've got 35 10 gigabit ports, how much connectivity do I need at a minimum back to the main spine? 350, 35 times 10. In this example here, you can see I've got 400 gigabits of interconnection total. So this Netgear switch in the middle, it has 32 100 gigabit ports. The switches on the side there each have up to 8 100 gigabit ports. How what? That's just what the port is. Yeah, it's what's called a QSFP. Right, so it's a fiber optic QSFP. Usually when the switches are all in the same rack, they won't actually use fiber optic. They use something called a direct attached cable, which is just copper, but with a QSFP on either end, like a 1 meter cable, 2 meter cable. But they could use fiber optic as well, or the switches could be in completely different rooms running over fiber in that case. So it's QSFP to either single or multi-mode fiber to the other end to a QSFP. Good question, thanks. So switch number 2 also has 35 encoders coming into it, so 400 gigabits going there. Switch number 3 is decoders. Has decoders numbers 1 to 38. So up to 380 gigabits needed. Again, we still have 400 gigabits, so we're good. Switch number 4, decoders number 39 to 76. So what's that, another 38 or so decoders. So we've got 400 gigabits connecting there. And then switch number 5 has decoders 77 to 113. So about another, 36, 37 decoders. So again, 400 gigabits of interconnectivity for that. So this is a design where anything can go anywhere, anytime, because you've got enough bandwidth from the leaves into the core. Then the core is completely non-blocking, of course. It can distribute those signals to any of the other switches. In this case, it'd be going to switches 3, 4, or 5. There'd be no data going from like switch 1 to switch 2 because both of those just have encoders connected to them and no decoders. Any questions here? Again, it's just basic math, making sure you've got enough bandwidth to handle what your interconnect needs to be, you know, based on your number of encoders or number of decoders. And I forget which customer this was, but it's not important. All right, this is what I'm calling a limited connection example. This is where you know some additional information about the design. This design was a casino, and they broke the casino into two different areas. If we look up at switch number 1 on the top there, that's got 24 encoders and 40 decoders into that 96 port switch. And that area was segregated, meaning that was an independent area. Those 24 encoders are only going to those 40 displays. They're not going anyplace else. So we've got the interconnect between switch number 1 and switch number 2, and it's only a 10 gigabit link. So you're not transferring any video data over that link. You're just sending control data. And 10 gigabits is way more than enough you're ever going to need for control. Okay? Down the bottom, we've got another 24, 25 encoders 25 to 48, that are going over fiber optic cable to another area of the facility connected to about 50 decoders. Decoders 41 to 90. Okay, so based on 24, 25 encoders, we should be planning for 240 gigabits of interconnect between those two switches. However, in this environment, we know for a fact that they're not transmitting any 4K data. Everything is 1080p. So each stream is only 3.2 gigabits maximum. So you take the 3.2 times 24, and that's what, approximately 75 to 80 gigabits. We put 160 gigabits in, and we've actually got way more than we need. And what's great about this is these switches have enough ports to expand. So in the future, let's say that this facility moves to 4K, they just need to add a couple more fiber optic lines between the two switches there to accommodate the extra bandwidth. Okay. Let's see the next design. Any questions? No? Okay. All right. This is a simple one. This is 2 switches, a dual switch design with a lag in between. Really, it could be a stack or a lag in this case because it's so simple. The switch to the left has 8 sources and 36 displays. And the switch to the right has 2 sources and about another 6 or 7 displays. 7. So here's a case where you're not looking at the decoders at all. You're just looking at the encoders. So if there's 8 encoders on the left and 2 encoders on the right, what's the maximum bandwidth I would ever need between the two, assuming, again, worst case? And the answer is going to be 80. So it's the 8 encoders going from left to right. So we set up 80 gigabits of interconnect between the two switches. Going from right to left, because there's only 2 encoders, the most we would ever need is 20 gigabits. So we know that 80 is still going to be fine. The decoders, again, don't matter. Everything on that switch to the left, same switch, non-blocking backplane, never have a problem. As long as I can get those 8 streams to the right, I'm good. Same thing on the right, never have to worry about those decoders from those 2 encoders, non-blocking backplane, and as long as I can get those streams to the left, I'm good. Again, this could be as a lag, or it could be, as a, gee, why am I drawing a blank? That's what you do when you do too many classes in one day. I'm just going to back up because my brain is fried. Thank you, stack. All right, let's look at the next one after this. A dual spine example. So here we've got two spines. Again, this is another example where they wanted everything to go everywhere, anytime. So we had to assume worst case scenario. And they had everything in one place, thankfully. So we didn't have to run fiber optic cable between the two. They kind of did this to give a level of redundancy. There's not a lot of redundancy here, but there's a level of redundancy. And that we've got, on the left there, if I look close, that top switch has 24 encoders and 15 decoders, and the switch underneath that was 23 and 13. So with 24 encoders, the maximum, I should be planning for is 240. We actually did 360 gigabits of interconnect back to those spines. Now on the right, I've got, 24 and 15, and 23 and 14. So again, we kind of went overkill on this with 320 gigabit into each spine. And that gives some room to expand the system as well, because both of those switches, or all four of those pink switches there, have more ports available. So if they want to expand the system, they can. And then, kind of again, you're doing some math. How much bandwidth do I need running between the two spines with, I got 47 encoders on one side and 47 encoders on the left. So roughly, it's 470, call it 500, make it 600 to be safe. So we had 600 gigabits interconnection in between. Now, if one spine were to go down, the left half of the network would continue to, if the right one went down, the left half would keep working. If the right went down, and vice versa. So a teeny bit of redundancy. It's not a completely redundant network. I'll show you one that is in a little bit. All right, this is an interesting one. This was actually relatively recent. This is a law firm in New York City, where they have it broken into two pieces, what they call the north rack and the south rack. Actually, the south is on the left and the north is on the right in this drawing here. So, and everything in north needed to be able to go to everything else in north, and everything in south had to be able to go anywhere in south. But they didn't really care too much about sending data between north and south, just limited. So we ensured that we had enough bandwidth between. So at the very top switch here, on each side is a spine. So the four switches underneath it each connect back to that spine. Then the two spines, like the previous slide, are connecting to each other. So there's plenty of bandwidth within each north and south, and then that 80 gigabits allows them to send a few streams between the two, but that's all they needed. And this also illustrates a case where we first designed this deployment with different switches. And then they said, this actually is very recent. So this came about in the summertime. They said, we want to deploy this in October. And we designed it, and then we went out and said, we can't get the switches we want in October. Basically it was 3 months away. So we found what we could get. And we redesigned the network, working with Netgear to meet the customer's needs. And, sometimes that happens. You work with what you got. You work with what you're able to get your hands on. All right, this is one of my favorites. This is actually a redundant dual spine design. This is the, as it says there, the Westgate. So this is the Westgate Hotel and Casino. This is a place that doesn't close. They're open 24 hours a day, 7 days a week. The betting office actually does close when there are no games going on, but the equipment never shuts down. It runs continuously. So they ended up with, and I forget the total quantity of devices here, I don't have it in the thing, but 2 spine switches, which are the 2 big blue ones. And then they had 9 smaller switches interconnected, where each of those connections is 100 gigabits. So they have 300 gigabits of data going from each of those leafs to each of the spines. So kind of the top spine and the bottom spines. Everything's connected to both. And this provides a lot of redundancy to the system. I mean, if an individual switch in the middle goes down, there's not much you can do about it. You know, any displays or encoders connected to that are going to go offline. But if one of the spines went down, the system would keep working. And this actually happened. One of the spines died completely, and the Westgate didn't even know that it happened. For how long, I don't know. Eventually, they discovered that one of the switches was down. The integrator went in, swapped the switch out, and you know, everything was still fine. So having that level of redundancy in this case really helped the casino, because you know, if the sports book goes down, then there's a lot of revenue tied to that. So this is a good design. It's a couple hundred endpoints. They have a 220-foot wide video wall, 16 feet tall, 175 different multi-views. It's quite the deployment. All right. So within any AV system, I just put this slide in to talk about, it's possible to have multiple networks. You can have an AV network, which is all your encoders, your decoders. In this case, I'm calling it the AV network ZV. And we have our management server, the brains of the system, which is controlling that AV network, or at least configuring that network and then providing a means of control. 99% of the time, the customer has installed a third-party control system. Crestron, AMX, Extron, QSys, whoever, right? We don't really care. We're compatible with everything. And oftentimes it's sitting on the AV network, and that's fine. But oftentimes they want to have it on a separate network. And to accomplish that, we've got our management server has what's called a dual NIC, 2 network interfaces. So it has a network interface to the AV network, and it has a network interface to the control network. So that control network can talk to the box, which can then control the things on the AV network. Very common. All right, I'm doing pretty good for time here. Any questions? Yeah.
Can the ZVs, encoder decoders work with different VLAN?
Can ZVs, encoders, decoders work on multi-VLANs? I mean, for them to see each other and stream to each other, they would need to be on the same VLAN.
VLAN 1 would be connecting to VLAN 2 with counter VLAN communication.
Well, you wouldn't normally have, I mean, it kind of defeats the purpose of separate VLANs if they're actually connected to each other.
Separate VLANs tends to limit the data flow between VLANs to another VLAN, but if they are need to go from one VLAN to another VLAN.
Right, I mean, so now you're talking, so when you're jumping between LANs, usually you're talking about having a router. And in some AV environments, you can send data through a router without a problem. You can do that with the ZV equipment. If, and this gets complicated, this gets into complicated network issues, all of the streams in an AV network environment are what's called a multicast. And multicast is great, and multicast is also really difficult at the same time, because you can run into this concept of either A, flooding a network with the multicast if it's not configured properly, flooding an interlink, which is probably the most common way to flood something. You're not going to flood a single switch usually. Or the concept of a multicast not being able to reach its destination. And that's the case when you get a router involved going between 2 LANs. So you need to have a network engineer involved that can say, these are the multicasts that I care about. I want them to pass from the router from this LAN to this LAN. So they need to configure that. And then there's also the issue of the management server being able to see the devices on both LANs. Okay, so that router needs to be configured also to be able to pass the control signals between the LANs as well. So we don't have many deployments that do that. We have a few. You always need a professional network person to make it work though. Because one thing the ZV will do, we'll help you design the network for you, but we're not going to make it work for you, if you know what I mean. It's up to the integrator to make the network work. We'll help you, give you, helps, tips, advice, but we're not going to go on site. We're not going to configure the network for you. There's a bazillion different manufacturers of network equipment. We're not experts on any of them. We really like Netgear. Aside from that, you're kind of on your own, other than all the documentation we can provide you about what you're supposed to do. Let's jump in. Okay. Yeah. Hops, so hop limit. The hop limit is going to depend on lots of different things. There's never a hop limit between switches. Okay? You have as many switches on the same LAN as you want. That doesn't imply a hop. A hop is when you're going from one LAN to another LAN. And yes, there is a limit. You're never going to hit it. If you've hit our hop limit, which is 32, you've designed a network so convoluted and insane that you should probably just start over. Okay, nobody's doing that. 32 hops through 32 routers to 32 LANs. Our support team would not like you. So the final little piece here, this is pretty short, kind of some network design prep. Keep calm and make a plan. Know what you're getting into before you get on site with a customer. So, as always, plan to use non-blocking switches. There's no reason not to. It's really hard to find a switch that is blocking these days. Review the documentation on switch requirements. We provide all this documentation on our website. Things like IGMP, fast leave, queryers, things of that nature. We tell you all the settings you're going to need. List out the location and quantity of encoders. Again, we talked about the direction the data flows out of an encoder into a switch. List out the location and quantity of decoders, remembering that decoders flow out of the switch to the decoder. Add the total quantity of encoders and decoders. And if it's less than a single switch, awesome, easy design. Determine if every source needs to route to every display. Sometimes they don't. That's often the case that they don't. So that can have design considerations. Create a high-level diagram of your network. This can just be a simple drawing. Determine, this is the important part, determine the needed bandwidth between your switches. How much bandwidth do I need based on the number of encoders and number of decoders? Do it for the worst case scenario. Then there could be a special needed work case scenario. Is it 4K? Is it only 1080p? That can be a big difference. Difference between 6 to 8 gigabits for a stream versus 3 gigabits for a stream. Huge difference in the amount of data. Don't be afraid to ask for help. As I said, we will review any design with you from a bandwidth perspective. But as I mentioned before, we do not take responsibility for making it work. That's up to you. Netgear, this is great. If you're using their switches, they offer free AV design review services. So you send them an email to proavdesign@netgear.com, and they will help you. They'll extensively help you. Basically, they'll design the entire network for you. Just some miscellaneous topics. This is kind of review stuff here. So is it a dedicated AV network or a shared network? Honestly, in our world, especially in the 10 gig world, it's always a dedicated AV network. It's never a shared network. Are you using just LANs, or you do have VLANs getting involved? Again, most of the time we're talking about a single LAN. VLANs very rarely come into play. PoE, love PoE. We have products that are 10 gig PoE. There are 10 gig PoE switches out there. If you can use PoE, use PoE. But don't forget your budget. Copper versus fiber. We didn't really talk about this much today, but we offer solutions where the interface is copper, RJ45, and we offer interfaces that are fiber, SFPs. So copper runs up to about 100 meters. Fiber, you can run up to 10 kilometers. So this all comes on your deployment. We do a lot of deployments in if you did a building like this is a massive convention center. I don't know what the AV closet is potentially, but you could have a need for fiber in this building. Whereas, if you're in just a small environment, copper can be fine if you're running less than 100 meters. And always think about your AV control system. What are you familiar with? What do your customers want? What are the capabilities you need to present to your customer? All right, this question comes up a lot. Who do we recommend? Who does ZV recommend for a switch? So really, we're what I call switch agnostic. Meaning we can work with any switch manufacturer out there as long as they meet the minimum capabilities. For example, if you're doing a 10 gigabit network, it has to be a 10 gigabit switch. You can't run it on a 1 gigabit switch. It needs to support some basic things like IGMP and fast leave and a query, things like that. But again, we detail all this in our documentation, and all of these companies make switches that meet those requirements. Netgear. As I mentioned Netgear a bunch of times, it's in almost all my examples. They are my favorite. They decided a few years ago to really dive into the AV marketplace with their switches. So they have pre-configured their switches, their M4250 line, M4300, M4500 series, to be really plug and play. They're pre-configured with all the settings that you need for AV equipment. Those product lines have a lifetime warranty. You can do solutions from as low as 8 up to over 600 endpoints. So regardless of the size of the deployment you need, they can have a solution for you. I mentioned earlier that they've that free network design services and installation support, that ProAVDesign at netgear.com. And these guys are really knowledgeable, and they're worldwide. So you send an email, you're going to get a response from somebody relatively local to your time zone. In the US, Europe, Asia, they have people everywhere. So you're not going to be waiting, a day because, it's just one guy in San Francisco. It's not. All right, that's kind of the end. So I'll say thank you, and any final questions before we wrap up our day? Yeah. Of course.
I see that you guys are actually talking about Netgears all the time, right?
Yeah.
I see that the M4300,
Mm-hmm.
most of the switches does not have PoE plus. Do your installations does not require PoE all the time?
So Netgear, good question. So in the 4300 series from Netgear, they offer both 1 gig and 10 gig solutions. Their 1 gig solutions are all PoE plus that I recommend. So ZV has a series of 1 gig solutions, and all of our products are PoE. So they all work just great, no problem. And all of our stuff is very low power use. Typically we're in the 6 to 8 watt land for power for our devices. So it doesn't even come close to hitting a PoE budget, even if you fill up the entire switch. They do have some 10 gig PoE devices. They have very limited, actually, 10 gig solutions. They've got a 16 port switch, which actually is really hard to get right now. And they've got their 96 port switch, where 48 of the ports can be PoE plus, 10 gig. And that's a great switch. And we have a product that's a 10 gig PoE solution. So if you can get your hands on it, I highly recommend it. But by most, I mean 98% of my 10 gig deployments are not PoE, just because there aren't that many 10 gig PoE switches out there yet. Netgear's got a whole new line of them coming out next year. I don't know the timing, but probably in the summer. All right, thanks everybody. Oh, questions?
One is, I noticed that you used the phrase encoding and decoding a lot.
Yes.
Would you be able to use transmitting and receiving as just an alternative?
Yeah, encoder, decoder, transmitter, receiver, TX, RX.
And then the second question is just, how are the lead times for the equipment at the moment for Netgear?
How are the lag times? Or?
The lead times?
Oh, lead times for product.
Like, for example, the 48 ports or the 24 ports.
Well, I can't speak for Netgear and their lead times. I can speak for our products. As a general rule, ZV, we're very good in terms of our stocking situation. 6 to 8 weeks for our encoders and decoder products, which these days that's is practically nothing. Yeah, I mean, I'm hearing some competing products 1+ year out for things. Dante devices are really hard to come by these days right now. I mean, I didn't talk about Dante at all. It's not relevant to what we were doing. But yeah, Audinate's had a hard time with their Ultimo and Brooklyn chipsets, getting devices out. And that's impacted us because we have devices that have those chipsets integrated in them. So those have been really hard to come by. Yeah, it's rough out there for a lot of things. So I know Cisco's having a really hard time with their switches. They're more than a year out. The design that I showed you in New York City at the law firm, that number one, it was going to be Cisco, but Cisco was a year out, so that went out the door. Then we went to Netgear and designed it, and then we realized we couldn't get those particular Netgear switches, and then the design they went with was the third design, which was the second Netgear design. Because we finally found some stuff that we could get. You always need the ZMP. Because that's talking to the ZMP. A Crestron, a QSys, a whoever cannot talk to our endpoints directly, can only talk to the ZMP. Dude, that question comes up a lot. Right. Right. I mean, they have, Crestron with their NVX has their director, which is not the greatest thing in the universe, but it's something. But you can also directly interface to an NVX endpoint without the need for anything if you want to. Again, that's difficult at best. Great. All right, thanks again, everybody. We're at booth Z11 if you want to stop by, demo or anything. We'll be there for another hour today, and then we're here all day tomorrow.